Perfect. So we're almost done. So we have out of the three measures of association that I wanted to teach you for this lecture. And the final one is called the correlation, the famous correlation. And the correlation has a particular statistic that is called the Pearson's R. And as you know, the correlation is usually related to this scatter plot in which you have the values of two numeric variables. That's the main difference between the correlation and lambda and Summers that you have here, or one of the main differences that you have here, two numeric variables. And the correlation tells you very quickly the direction of that relationship and the strength of that relationship. Okay? For instance, in this case, we want to know if there is any, or what is the kind of relationship that has a college, like countries that have different percentages of college, or the population were highly educated. What is the relationship with that variable and voter turnout in that country? Okay, and we can see here that the relationship is positive and is very strong. Okay. It is important to mention that the formula of Pearson's R is basically the standardization of the independent variable, or x, and the standardization of the dependent variable divided by the size of the sample. Okay. So we want to have here, because when we are talking about the standardization, is because we want to find C values, for instance, in this case. So we want to have C values for X and C values for Y. And with those C values, we can actually estimate if that relationship is positive, negative, and the strength of that relationship. And we use this particular type of scatter plot in which you have four quadrants. The quadrant in the top left and the quadrant in the lower right, which is 1 and 3, actually will provide negative values, because you have here, for instance, if this is X, you have negative values of X and positive values of Y. And here you have the opposite, positive values of X and negative values of Y. And for that reason, you will have negative values here. The quadrants 2 and 4, which are the lower left and the upper right, will give you positive values, because you have, in both cases, values with the same sign. And this is important because if the combination of values 2, 4 predominate, then the relationship will be positive and strong, right? If it is something like this, such as in this case, actually, you're going to have a relationship that is positive and strong. If it is the opposite, like this, you're going to have a negative relationship and strong, okay? If the scores are equally dispersed across the four quadrants, if you find something like this everywhere, so you're going to have a very weak relationship, okay? Just to show you, so when the Pearson's R takes the value of 0, you're going to see something like this, dispersion. A dispersion across all the quadrants of the scatter plot, okay? When the relationship, or when the value is close to +1, you're going to see something like this. And when the value is close to minus or -1, you're going to see something like this, like a negative relationship. Okay? Values that have an absolute value of 0.5 or higher are a signal of a moderate or kind of relatively strong relationship between the two variables. Okay? Even if the correlation coefficient is very popular and very, to some extent, is also kind of powerful to describe the relationship between two variables, it has crucial limitations. One of them is that this is not an asymmetrical measure of association, so it has no causal explicative power. And that's the reason of why people always say this cliche of the correlation does not mean causation, right? So it's because you see that there is a strong connection between the two variables, but you cannot tell why or which one is creating the other one, okay? The second limitation is it is not a proportional reduction in error measure of association, which means that you cannot predict the dependent variable because you don't know what is the dependent variable, but you cannot predict one of the variables with the other variable, okay? Now, correlation in R is very simple to estimate it. Actually, the function that we use is part of the the basic functions or canned functions of R. So you don't need to download any other package to use the function to estimate correlation. But what we're gonna do here is that we're gonna use the dataset gapminder that is attached to the package DSLabs. And we have used it in the past, okay? I'm gonna delete all the missing values because if you use missing values, you're gonna see kind of error. So you want to omit that. So I created a new object called GM. And imagine that we want to explore the relationship between rates of fertility and rates of infant mortality in, I don't know, in a cross-national setting, okay? So we use the function. This is the function, is basically core. This is the main function. And these are your two variables. The order of the variables don't really matter because you're not telling R that one of the variables is the independent or independent variable. You cannot do it with a correlation. And this is the result. So you have here a positive, strong correlation between the two variables, okay? But you cannot say anything else. But that's still very powerful, okay? Okay, guys, so those are the three measures of association. Now, as a summary, how do you choose one measure of association? The basic answer to that question is that you need to pay attention to what are the scale of measurement of your variables of interest, okay? Especially or usually the most important thing here is the dependent variable, okay? So you're gonna use the t-test and the Pearson's R or correlation when you have numeric dependent variables, okay? You're gonna use the proportion test and summers when you have ordinal variables. And you're gonna use the proportion test and lambda when you have nominal variables. And you can also use for categorical variables, either if they are ordinal or nominal. You can also use the key test if you want to examine the independence of the two variables, including all the categories, okay? So it's very simple. So you just need to keep in mind that, especially for the applied project and in the future, so I need to estimate something related with a numeric dependent variable. Okay, so I'm gonna use these, the t-test and the correlation. And I'm gonna use a nominal kind of variable, so I'm gonna use the proportion test and lambda, and so on and so forth, okay? Now, let's finish this lecture, this very long lecture, with some of the limitations of the bivariate inferential statistics. And I think one of the first problems is that the null hypothesis is really not the most important thing that we want to debunk, or is not the most important thing that we want to do with inferential statistics. It's just the first step. Okay, so we of course we need to debunk the null hypothesis in order to be confident that our effects are strong and are not produced by chance, but are to some extent between quotation marks real. But the actual challenge is either to debunk a rival explanation, a real rival explanation, or to provide evidence that our explanatory variable has an effect on y, even if some other variables are present. And that's why we control by C or by third factors or other explanatory variables. Okay? So again, we want to debunk the null hypothesis. That's an important, but that's just the first step. We usually want to say that our theory or our hypothesis or the variable that we are proposing as the main explanatory variable has stronger explanatory power than rival explanations, or we want to say, okay, even if those other rival explanations are present, our variable also helps to explain our outcome of interest. Okay? The second limitation is that the bivariate analysis, as it is said in this, or this kind of bivariate analysis, tell us nothing about other variables. So remember the problem of internal threats or threats to internal validity, or this idea that there might be other factors that actually explain our outcome of interest. And because we are using just two variables, our x and our y, we're not really controlling for all other potential factors. That's like a huge limitation of this kind of bivariate analysis. Okay? So if you want to go with one of these, or you need to use a couple of or a pair of these methods of bivariate differential statistics, if you want to, for instance, use the t-test and the correlation, you also need to complement that analysis with these advanced techniques of descriptive statistics that I taught you, that help you to some extent to see what happens if you control for a third variable. Okay? But it's often cumbersome to have these two separated methods to estimate the statistical and the substantial significance. The good news is that the linear regression that we're going to learn next week is going to help us with these two things. It's going to help us with problems of threats to internal validity and with problems of threats to external validity. Okay, so it's going to give you the linear regression coefficient is going to tell you if the relationship between x and y is significant, and if it is statistically significant is what I mean. It's going to tell you the strength of that relationship, and also it's going to allow you to control for C, and not only for one additional variable, but for several variables. Of course, this has a cost, but it's very useful. Okay, guys. So thank you so much. Of course, you're gonna have questions. I expect those questions. But the key thing is this: you need to know to have. Okay, so you need to process several things that I have told you in this long lecture, but you also need to be pragmatic. Okay, so you need to understand a thing that you feel very comfortable with the logic of the bivariate analysis, especially with what really means to be statistically significant. Okay, so what is the rule? The role of the null hypothesis, and why do we need to debunk the null hypothesis, and how do we do it? So that's important. And what I want you to feel confident right now with the test of significance is to know, okay, I have this kind of variable that is, for instance, a nominal variable. What kind of test of significance I can use and I need to use, okay? And in addition to that, how do I interpret the results of that test? Okay, I'm not gonna ask you anything, and I don't care about mathematical estimation. So you don't need to know too much about the formulas or whatever. I explain the formulas because I think it's important that you have an intuitive, like a kind of understanding of how's the mechanics of this formula, and how is this formula set, and you can understand several things when you understand better the formula, okay? But that's not the main thing here. And remember that the mathematical procedures can be conducted by R or by other statistical software, okay? So that's the first part. The second part is that you need to understand what is the role of measures of association. What is this thing called proportional reduction error? To understand what it means. What it means is that basically what you're saying here is, okay, you're always gonna make errors between quotation marks, predictive errors. Basically, what you want to know is what happens if you know the value of the independent variable. You're gonna reduce the number of errors. If you do it, if you reduce it, the number of errors, then you're gonna have higher predictive capacity of the dependent variable. Okay, that's the goal of the measures of association, and you need to have that clear in your mind. And similar to the significant test, what I ask you to know about the measures of association is, okay, there are these three different measures of association that I learned this class, and if I have this type of dependent variable, what kind of measure of association can I use? Okay, again, don't worry about mathematical estimation. So you have 6 methods. I know it's a lot, but if you have that clear, you're gonna be fine. Okay, the quiz is gonna be this time even easier. I'm gonna ask you something very simple, so if you have clear in your mind these basic concepts, so you're gonna do it, you're gonna be fine. Okay, and keep processing this, because this is going to be useful if you want to use these methods, this kind of bivariate differential statistics, for the applied project, for the final part of the applied project. Okay, thank you so much. Thank you for watching this long video. Bye.